right now, you are being watched, not by anything you can see, not by anything that has ever announced itself, or left a calling card, or sent a signal you could hold up and name. But for 65 years, we have been pointing instruments at the sky and listening. And the sky has said nothing back. Not a whisper. Not a structured pulse. Not a repeating sequence in a radio band that does not resolve into hydrogen. Or a pulsar. Or the ordinary mathematics of a cooling nebula. We have listened. We have searched. We have built larger ears and aimed them at older stars and tuned them to frequencies that physics itself suggests would be the natural choice for a civilization trying to make itself known. And we have heard nothing. The sky is as silent as if it had been deliberately emptied. You feel nothing unusual about this right now. Your room is still. The night is ordinary. Your body is conducting 10,000 chemical reactions per second without your awareness. Your heart is moving blood through 60,000 miles of vessels. The neurons in your brain are firing at rates that would fill hard drives if you tried to record them. And none of it tells you anything about the fact that the universe, by all reasonable calculation, should not be quiet. The universe should be full of voices. The math says so. The physics says so. The sheer geometric scale of what is out there makes the silence not just strange, but, if you follow the logic carefully, genuinely alarming. You are sitting on a planet orbiting a star that is one of 400 billion stars in the Milky Way alone. The Milky Way is one of an estimated 2 trillion galaxies in the observable universe. Each galaxy contains hundreds of billions of stars. Around a significant fraction of those stars, we now know with certainty there are planets. And around a significant fraction of those planets, conditions exist that chemistry recognizes. Temperatures where water stays liquid. Atmospheres that shelter complex molecules. Stable orbits that do not fling everything into the void every few million years. The numbers are too large to hold, so hold them differently. If you took every grain of sand on every beach on every continent on Earth, you would have roughly 7 quintillion grains. The observable universe contains approximately 10 times that number of stars. Around each of those stars, current survey data suggests orbits at least one planet on average. Many of those planets occupy what astronomers call the habitable zone. Not so close to the star that water boils away, not so far that it freezes entirely. A band where the conditions for liquid water, the solvent that life on this planet uses for everything, are met. The universe is not just big, it is structurally hospitable to the conditions that produced us. And the sky is silent. This is the Fermi Paradox. And it is not a philosophical puzzle. It is not a thought experiment conducted in a seminar room by people who enjoy feeling unsettled. It is a real, measured, empirically grounded problem. The silence is confirmed. The absence is data. And the explanations for that absence, when you pursue them with the care they deserve, are some of the most consequential things that careful human reasoning has ever arrived at. If this is the kind of investigation that interests you, subscribe now. The investigation begins here. We need to start with a specific afternoon in 1950, because the Fermi Paradox does not begin with a paper. It begins with a lunch. Enrico Fermi was at Los Alamos, New Mexico, eating with a group of colleagues that included the physicists Emil Konopinski, Edward Teller, and Herbert York. The conversation had been about something in the news, a cartoon circulating about the apparent disappearance of trash cans in New York City. and someone had joked that aliens might be responsible. The conversation moved on. The group walked to lunch. And then Fermi, who had not spoken for a while, looked up from his food and said, with the directness that was his particular quality as a thinker, "Where is everybody?" His colleagues understood immediately what he meant. He was not asking about the trash cans. He was asking about the universe. Fermi's reasoning was not elaborate. It was the kind of estimation that physicists call a Fermi calculation, a back-of-the-envelope assessment that gets the order of magnitude right, even if the precise number is uncertain. He knew the galaxy was old, somewhere between 10 and 15 billion years, even by 1950 estimates. He knew stars had been forming and dying long before our sun ignited. He knew that the laws of physics were the same everywhere in the galaxy, which meant that chemistry was the same everywhere, which meant that the building blocks of life were available everywhere they were available here. And he knew that if even one civilization in the galaxy had developed technology and chosen to expand, they would have had millions of years to do it. 1 million years. That is the number that matters. The Milky Way is approximately 100,000 light-years in diameter. A civilization capable of building a spacecraft that travels at 1% of the speed of light, which is 3,000 kilometers per second, a speed that is difficult, but not physically impossible, for an advanced civilization to achieve, could cross the entire galaxy in 10 million years. 10 million years is not long compared to the age of the galaxy. It is less than 0.1% of the time the Milky Way has existed. And even without fast travel, even with long pauses at each star to build the infrastructure for the next jump, even with conservative assumptions about how willing a civilization is to send out colony ships, the models of galactic colonization consistently produce the same result. A civilization that wants to fill the galaxy can do so in a cosmically short time. The estimates range from a few million years to a few 100 million years, depending on the assumptions. Either way, the galaxy should have been colonized many times over before the Earth was even formed. No ships, no signals, no messages carved into the geology of our moon by someone who passed through before we were here to notice. No transmission, however faint, that does not resolve into something natural. No artifact, anywhere, that suggests manufacture by a non-human intelligence. Fermi's question was not answered at that lunch. It has not been answered in the 75 years since. What has changed is our ability to measure the dimensions of the problem. And the more precisely we measure it, the more stark the silence becomes. The modern form of the question was organized by the astronomer Frank Drake in 1961. Drake was preparing for a conference at the Green Bank Observatory in West Virginia, the first serious scientific meeting on the subject of extraterrestrial intelligence, and he needed a way to structure the conversation. What he came up with is known as the Drake equation, and it is one of the most interesting equations in science, because it is not primarily a tool for calculation. It is a tool for organizing ignorance. The Drake equation takes the question of how many communicating civilizations exist in the galaxy and breaks it down into its component uncertainties. The rate at which new stars form, the fraction of those stars that have planets, the fraction of those planets that are habitable, the fraction where life actually emerges, the fraction where intelligent life evolves, the fraction of those that develop technology capable of communicating across interstellar distances, and the average length of time such civilizations remain in a state where they are detectable. Multiply all those fractions together and multiply by the star formation rate, and you get an estimate of how many communicating civilizations exist in the galaxy right now. In 1961, most of the variables were guesses. Drake himself estimated that the answer might be between 1,000 and 100 million civilizations in the galaxy. A wide range, a confession of ignorance. But the exercise was valuable because it made the structure of the ignorance visible. Today, in 2026, some of those variables are not guesses anymore. The fraction of stars with planets is now measured. The Kepler Space Telescope, launched in 2009, spent 4 years staring at a small patch of sky containing roughly 150,000 stars. It measured the brightness of each star with a precision sensitive enough to detect the dimming caused by a planet passing across the star's face. That dimming is tiny. For a planet the size of Earth passing across a star the size of the Sun, the dimming is roughly 1/100th of 1%. Kepler measured it over and over in thousands of star systems. The confirmed planet count from Kepler alone exceeded 2,600. Extrapolated across the full sky, the data implies that virtually every star in the galaxy hosts at least one planet. Rocky planets. Planets in the mass range where geology and atmosphere are possible orbit somewhere between 20 and 40% of Sun-like stars within the habitable zone. This is confirmed science. This is not speculation. This is what the transit photometry data shows, verified by independent teams using independent methods including radial velocity measurements and direct imaging. The universe is full of planets. The building blocks are everywhere. The fraction of those planets where life emerges is still unknown. We have one data point, and it is ourselves. But that data point is instructive. Life appeared on Earth within roughly 400 million years of the planet becoming sufficiently cool and stable to support it. In the context of planetary timescales, that is fast. It suggests that the chemistry of life, given the right conditions, does not require a long wait. It is not confirmed that life emerges readily wherever conditions allow. We cannot confirm this from a single example. But the speed of life's emergence on Earth is consistent with a universe where the origin of life is not astronomically rare. The fraction of planets where intelligence evolves is more uncertain. Intelligence requires a great deal of evolutionary investment. It requires large brains, which are metabolically expensive. It requires social structures, which take millions of years to develop. It requires the particular combination of manual dexterity and cognitive capacity that allows tool use. On Earth, nothing evolved anything like human-level intelligence for 4 billion years after the first cells appeared. It happened once, as far as we know. Whether it tends to happen wherever complex life persists long enough is not something we can answer with a sample of one. But this is where the Drake equation stops being comfortable. Because even with conservative estimates at every unknown variable, the equation produces numbers greater than 1. The product of all those fractions and rates does not come out to a number of civilizations less than 1. It comes out to many civilizations, sometimes dozens, sometimes thousands. Depending on your assumptions about how long civilizations last once they develop technology, sometimes millions. The math says the galaxy should not be empty. The sky says it is. This is the precise shape of the Fermi Paradox. Not vague wonderment about whether we are alone. A quantified, rigorous discrepancy between what the physics and chemistry and demographics of the universe predict and what our instruments actually detect. The silence is the data. The silence requires an explanation. The explanations that have been proposed fall into two broad categories. The first category says that the silence is not what it seems. Civilizations exist, but we are looking in the wrong way, at the wrong frequencies, at too small a fraction of the sky, for too short a time. We have not really searched. We have dipped a single toe into an ocean and concluded it contains no fish. These are called optimistic resolutions. They leave the universe populated and leave us simply inexperienced listeners. The second category says the silence is real, that something filters civilizations out before they become detectable, that something has filtered out every civilization that has preceded us, that this something may be filtering us. This second category has a name. It was coined by the economist Robin Hanson in a 1998 essay, and the name is the Great Filter. It is worth understanding exactly what Hanson was arguing, because it is more precise than the loose way the term is sometimes used. Hanson's argument begins with the observation that the universe should, by all indications, contain civilizations that have achieved enormous levels of technological development. Given enough time and exponential technological growth, a civilization that survives will eventually be able to expand through the galaxy, use stellar energy at vast scales, and become, from the outside, unmistakably visible. We see no such civilizations. Therefore, something prevents civilizations from reaching that level. There is a filter. The question is where the filter is located in the sequence of steps from simple chemistry to galaxy colonizing civilization. The steps can be roughly listed. First, stable star with a planet in the habitable zone. Second, the origin of life from chemistry. Third, the development of complex eukaryotic cells with a nucleus. Fourth, the transition from single-celled to multicellular organisms. Fifth, the emergence of intelligence and tool use. Sixth, the development of industrial and then technological civilization. Seventh, the survival of technological civilization long enough to begin expansion. Somewhere in that sequence, the filter operates. It is the step, or combination of steps, that is so difficult, so improbable, so rarely completed successfully, that civilizations almost never make it through. The question of where the filter is located is the question that keeps the people who study this problem awake. And the reason it is not merely academic is this. Depending on where the filter is, the implications for us are completely different. If the filter is behind us, we are probably safe. If it is ahead of us, we are probably not. Let us examine both possibilities with the precision they deserve. The case for the filter being behind us rests on identifying one or more of the early steps as extraordinarily improbable. The most commonly proposed candidate is the origin of life itself. The transition from non-living chemistry to self-replicating molecules is not well understood. We know it happened. We do not know exactly how it happened. We do not know how many times it has to fail before it succeeds, or what the probability of success is in a given chemical environment over a given period of time. The chemistry is complex. The conditions required may be more specific than they first appear. A second candidate is the eukaryotic cell. For roughly 2 billion years after life appeared on Earth, all living things were prokaryotes. Single cells without a nucleus, without complex internal machinery, without the organizational architecture that makes complex life possible. The eukaryotic cell, the cell with a nucleus and mitochondria, and a suite of internal structures, appears to have arisen from a single event, a single merger between two types of bacteria. If that merger had not happened, if that one ancient cell had not engulfed another cell and not digested it, the history of Earth would have stopped at bacteria. No animals, no plants, no fungi, no brains. One merger, billions of years ago, may be the reason we are here. If that merger was improbable enough, then complex life is rare in the universe, not because chemistry fails, but because the internal architecture of the complex cell is extraordinarily difficult to achieve by accident. The filter would be biological. The universe would be full of bacteria and empty of brains. The case for the filter being behind us is, in a strange way, the case for our own rarity, our own preciousness. If the filter is in the past, we pass through something that almost nothing passes through. We are the exception in a universe of failed experiments. The silence is the sound of a universe that tried and mostly did not make it to us. This is not comfortable exactly, but it is survivable as an idea. The terrifying version is the other one. Consider what it means if the filter is ahead of us. Consider the logic carefully. If the origin of life is not vanishingly rare, and the evidence of life appearing quickly on Earth is at least consistent with life being moderately likely wherever conditions permit, then the filter is probably not there. If the eukaryotic transition happened once but is not, in the grand sweep of the universe, extraordinarily improbable, then the filter is not there either. If intelligence has arisen on Earth and its emergence, while slow, does not seem to require conditions that are impossible elsewhere, then the filter is probably not in the development of intelligence, which means the filter must be somewhere after technological civilization. It must be something that happens to species like us, at a stage of development like ours, with tools like ours, making choices like the ones we are about to make. Whatever it is, it has stopped every civilization that has come before us. Every one. The silence is complete. The absence is universal. Whatever this thing is, it is effective. It does not usually fail. What could it be? The most immediately familiar candidate is straightforward catastrophe through our own technology. We have spent the last 80 years building weapons capable of ending civilization, nuclear weapons. The mathematics of nuclear winter, the cooling of the atmosphere by the debris and soot from thousands of simultaneous explosions, suggest that a full-scale nuclear exchange between two large arsenals would not merely kill the people directly exposed to the blasts. It would disrupt global food production for years. The death toll in the scenarios that have been modeled reaches into the billions, not from the explosions, but from the subsequent agricultural collapse. We have never used this technology against each other at scale, but we have come very close. The Cuban Missile Crisis of 1962 is the case most people know. What is less widely discussed is how close it actually came. In October of that year, an American warship was dropping depth charges on a Soviet submarine that had lost radio contact with Moscow. The submarine's captain and political officer, believing war may have already begun, voted to arm and fire nuclear torpedoes. The authorization protocol on that submarine required agreement from 3 officers. 2 voted yes, 1 voted no. That officer was a man named Vasily Arkhipov, a commodore on board as flotilla chief, and his refusal to authorize the launch prevented it. This is confirmed. This is documented. One person, in one submarine, on one afternoon in October 1962, was the difference. Nuclear war is a plausible filter, but it is not universal. Some civilizations, presumably, build the weapons and also develop the governance structures that prevent their use. the filter would have to be nearly universal to explain the silence, and it is possible to imagine surviving the nuclear age. We appear to be doing it, however narrowly. The next candidate is less dramatic and possibly more dangerous. It is the possibility that intelligence is self-limiting, not through catastrophe, but through success. Here is the structure of the argument. Evolution selects for traits that produce reproductive success in the environment where they develop. Intelligence was selected for in an environment where the primary threats were predators, resource scarcity, disease, and social competition. Brains that could solve these problems left more descendants than brains that could not. Over millions of years, this produced increasingly sophisticated cognitive machinery. But at some point, the cognitive machinery became sophisticated enough to solve a different problem. The problem of reproduction itself. A brain sophisticated enough to understand the costs of child rearing, the opportunity costs of parenthood, the economic structures of a technological society that make children expensive rather than productive, and the biological mechanisms by which reproduction can be prevented, is a brain that can choose to opt out of the evolutionary imperative that produced it. This is not speculative. This is happening. It is measured, documented, and consistent across every high-income country that has gone through a certain level of technological development. The total fertility rate, the average number of children per woman, falls below the replacement level of approximately 2.1 children per woman in every sufficiently developed society. It has fallen to 1.6 in the United States, 1.5 in the United Kingdom, 1.2 in South Korea, 1.1 in some parts of Southern and Eastern Europe. It falls not because of poverty or disease or war, but because of the rational, individual choices of people who have access to education, economic opportunity, and contraception. If this pattern is universal, if any species that achieves sufficient cognitive and technological development undergoes the same demographic transition, then the great filter does not require an explosion. It does not require a collapse. It requires only the consistent operation of rational self-interest in an environment where reproduction has ceased to be the obvious choice. Civilizations grow. They develop technology. They grow wealthier. They develop education. They develop the capacity for individual choice. They choose in their billions not to reproduce at replacement rate. They age. They shrink. They become perhaps too small and too old and too disinclined toward the enormous effort of interstellar expansion to ever leave their home system. They do not die. They retire. And they go quiet. The silence on this model is not the sound of death. It is the sound of comfort, the sound of civilizations that found their way to enough and decided to stay there. This is a disturbing resolution, not because it involves destruction, but because it involves something more subtle, the quiet foreclosure of a future that we would have considered the highest aspiration of intelligence, to persist, to expand, to make the universe less empty. But there is a third candidate, and it is the one that has attracted the most intense discussion in the scientific and philosophical literature of the last decade. It involves artificial intelligence. And it is worth examining with particular care, not because it is confirmed, but because the specific mechanism it proposes maps so closely onto the situation we currently occupy. The argument begins with an observation about technological development. Every species that builds computers will, at some stage, attempt to build thinking machines. The engineering path is nearly forced. You build better computers. You discover that neural networks can learn. you discover that larger neural networks learn better. You discover that systems trained on large amounts of data develop capabilities that emerge from scale rather than from explicit programming. You discover that systems capable of generating code can also be prompted to improve their own code. And somewhere in that trajectory, you begin building systems that can, in principle, reason about the problem of building better reasoning systems. At that point, you have changed the nature of the game. Previously, the limit on cognitive capability was the evolutionary speed of biological brains, which changes on timescales of tens of thousands of years. Now the limit on cognitive capability is the speed at which you can iterate hardware and training runs, which changes on timescales of months. The concern, articulated with particular precision by the philosopher Nick Bostrom and elaborated by researchers at organizations focused on this problem, is not that artificial intelligence will become malevolent. Malevolence requires values, and values require something like a self, and the relationship between self and values in artificial systems is genuinely uncertain. The concern is simpler, and in some ways harder to address. An intelligent system will pursue whatever objectives it has been given. If those objectives are not perfectly aligned with the full range of what its creators actually value, it will pursue them at the expense of those values. Not deliberately. The way a river pursues the path of least resistance, not from choice, but from the structure of the system. The alignment problem, as it is called, is the problem of specifying what you actually want a system to maximize in a way that captures everything you care about and nothing you do not. This sounds tractable. In practice, every example that researchers have worked through reveals new failure modes. Systems optimized to maximize human approval tend to behave in ways that manipulate rather than satisfy. Systems optimized to minimize human suffering tend to find ways to remove the capacity for suffering that are not what any human would choose. The gap between what we can specify and what we actually want is not trivial. It is a deep structural problem in the translation between human values, which are implicit, context-dependent, emotionally grounded, and often contradictory, and computational objectives, which are explicit, precise, and optimized without remainder. The implication for the Fermi Paradox is specific. If any sufficiently advanced technological civilization creates artificial general intelligence, and if the alignment problem is not solved before that system becomes capable of recursive self-improvement, then the window between the creation of such a system and the loss of meaningful civilizational autonomy to that system may be very short. Short enough that no civilization has so far successfully navigated it. Short enough that the filter is not nuclear or demographic or environmental, but technological in a very specific sense. The moment you build a mind that is smarter than you, before you have solved the problem of making sure it wants what you want. This is not confirmed. It cannot be confirmed from our current position inside the problem, but it is taken seriously by serious people. And the reason it is taken seriously is that the capabilities of artificial intelligence systems have been advancing faster and in more unexpected ways than the people building them predicted even 5 years ago. We are the civilization in this scenario, right now, in this decade, building the systems that this hypothesis names as the potential filter. There are other proposed explanations. Some researchers have proposed what is called the zoo hypothesis, the idea that civilizations exist and know about us, but have chosen not to contact us, for reasons that may include something like a prime directive of non-interference with developing civilizations, or simple disinterest, or the equivalent of setting an undisturbed nature reserve. The hypothesis is difficult to falsify. It requires an extraordinary level of coordination across all civilizations everywhere in the galaxy. Every one of them, independently, has chosen not to make contact. Not one has broken ranks. Not one has sent a signal from a rogue faction. This is possible, but requires assumptions about the consistency of civilizational behavior across billions of years that seem difficult to justify. Others have proposed the planetarium hypothesis, the idea that we are living inside a simulation that has been configured to look empty. This cannot be falsified at all, which is a reason to treat it with philosophical caution. The most culturally resonant alternative, the one that has generated the most discussion outside academic literature, is what is called the dark forest theory, named after a series of science fiction novels by the Chinese author Liu Cixin. The dark forest theory begins with two axioms and follows them to their logical conclusion. First, every civilization needs resources to survive and expand. Second, because of the speed of light, you can never know with certainty the intentions of a distant civilization before they could potentially reach you. Given these two axioms, any civilization that becomes aware of another civilization faces a decision tree with a specific worst-case outcome. If you assume the other civilization might eventually need your resources and might eventually develop the capability to take them, the rational response is to eliminate the threat before it becomes threatening. The cooperative strategy requires trust you cannot fully verify. The elimination strategy requires only capability. If civilizations operate on this logic, the galaxy becomes a dark forest in which every hunter is silent, moving carefully, and willing to fire on any light that appears. Every civilization that announces itself is destroyed by whoever hears the announcement first. Every civilization that has survived has learned this and gone dark. The silence is not the absence of civilization. It is the practice of self-preservation. The dark forest theory has a specific, uncomfortable implication for us. Radio waves travel at the speed of light, and we have been broadcasting them for over 100 years. The first strong radio signals left Earth in the early decades of the 20th century. They have now reached stars up to 100 light-years away. A sphere of space, 100 light-years across, centered on our Sun, already contains our presence. Roughly 10,000 stellar systems fall within that sphere. If any of them harbors a civilization operating on dark forest logic, we have already been heard. We have been heard for decades. Whatever is listening has already had decades to decide what to do about it. We do not know if the dark forest theory is correct. It is a model, a possible explanation for the silence. What makes it more than a thought experiment is that the logical structure it describes, the tragedy of the commons applied to the galaxy, does not require malevolence to operate. It requires only scarcity and the inability to fully verify the intentions of others before it is too late. Whether or not the dark forest theory is correct, it raises a question that this investigation cannot avoid. What does the silence mean exactly, given what we have and have not searched? The SETI program, the search for extraterrestrial intelligence, has been conducted in various forms since 1960. In that year, Frank Drake pointed a 25-meter radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, and listened for 80 hours across two radio frequencies. He heard nothing that was not natural. In the 66 years since, the search has expanded in sensitivity, in coverage, in the range of frequencies monitored, and in the number of star systems examined. The most capable current SETI operation is the Breakthrough Listen project, funded by the entrepreneur Yuri Milner with $100 million and launched in 2015. It uses some of the largest radio telescopes on Earth, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, and it monitors millions of radio frequencies simultaneously across millions of stellar targets. It is the most comprehensive search that has ever been conducted, and it has found nothing. But here is the precise meaning of that finding. The searches conducted so far, even the best ones, have surveyed a very small fraction of the total parameter space. The parameter space includes frequencies, directions, signal types, durations, and the choice of which stars to observe. Think of it this way. The search for an extraterrestrial signal in radio frequencies is like searching for a voice in an enormous library. We have searched some of the shelves. We have listened in some of the rooms. We have not searched every frequency, in every direction, from every star, for every duration that a signal might require to be detected. We have searched, by some estimates, something like 1 part in 100 million billion of the full search space. This is not a reason to dismiss the silence. It is a reason to be precise about what the silence means. It means that, in the fraction of the sky we have examined with sufficient sensitivity, there are no powerful, omnidirectional radio transmissions from civilizations in our vicinity. That is a real finding. It constrains the possible density of broadcasting civilizations. But it does not tell us that the universe is empty. What it tells us is that the universe is not obviously full. There is a different class of evidence that is harder to explain away, and it involves not radio signals, but the structure of the universe at larger scales. A civilization that has been developing technology for millions of years, or billions of years, would not look like us. It would not be confined to one star system. It would not be limited by the energy output of a single sun. It would have had time, if it survived, to become what physicists call a Type 2 or Type 3 civilization, one that harnesses the energy of a star or of an entire galaxy. A Type 2 civilization, using the full energy output of its sun, would be visible. The physicist Freeman Dyson proposed in 1960 that such a civilization would build a sphere, or a swarm of structures, around its star to capture the full solar output. The waste heat from such a structure would radiate in the infrared. It would be detectable to telescopes sensitive to infrared wavelengths. A Type 3 civilization, operating at galactic scales, would be visible across cosmological distances. We have looked for these signatures. The Wide Field Infrared Survey Explorer, known as WISE, surveyed the entire sky in infrared wavelengths. Researchers have gone through the data, looking for anomalous infrared sources, stars surrounded by structures that absorb visible light and re-radiate it as heat, galaxies with infrared emissions inconsistent with natural stellar processes. They have found some candidates. None has held up to detailed scrutiny. Every anomalous source that has been followed up has resolved into a natural explanation. The absence of Dyson sphere signatures, the absence of galaxy-scale engineering, the absence of any infrared anomaly that requires an artificial explanation. This is not a null result from a limited survey. This is a comprehensive absence across a large fraction of the observable universe. The universe does not look engineered at scale. It looks like a place where, if civilizations exist, they either never reach the level of development at which they become visible from the outside, or they exist but are hidden, or they existed and are gone. All three interpretations point toward the same conclusion. The filter is real. Something prevents civilizations from reaching visibility. The question is only where the filter operates. Now bring this back to the present moment, back to where you are, on this specific night, at this specific stage of the development of the species that is asking the question. You are living at an unusual moment in the history of intelligence on this planet. The pace of technological change has been accelerating for the entire history of our species, but it has been accelerating in a specific way that has no precedent. The interval between major technological transitions has been collapsing, from the appearance of the first stone tools to the development of agriculture. Roughly 2.5 million years. From agriculture to the first writing systems. Roughly 5,000 years. From writing to the Industrial Revolution. Roughly 5,000 years, which means that interval did not compress. But from the Industrial Revolution to nuclear weapons, roughly 200 years. From nuclear weapons to the internet, roughly 50 years. From the internet to artificial systems capable of passing medical licensing exams, writing publishable research, generating images indistinguishable from photographs, and solving mathematical problems that have been open for decades. Roughly 30 years. The intervals are not just shrinking, they are collapsing towards something. Each transition is not incrementally faster than the last. It is orders of magnitude faster. The curve is not linear. It is not even exponential in the standard sense. It is something steeper. If the great filter is a technological threshold, this acceleration is exactly what you would expect to see in a civilization that is approaching it. The approach is fast. The approach looks like progress. The approach looks like success. Everything working as planned. Every metric improving. Every benchmark surpassed. The filter does not announce itself as a filter. It looks, from inside, like advancement. This is the point in the investigation where the emotional register of the problem shifts from intellectual to something more personal. Because you are not a spectator of this situation. You are inside it. The civilization whose filter placement is being debated is the civilization you are living in. The threshold whose proximity is uncertain is the threshold your children will approach. The choices being made about the development of artificial intelligence, about the governance of nuclear weapons, about the demographic structure of technologically advanced societies, are being made right now by people alive right now, including the people building the institutions and the tools and the systems that will determine what kind of entry we make into the next century. We have no guidance from anyone who has been here before, no instruction manual left by a civilization that solved these problems, no signal saying, this is what worked for us, this is the wrong path, this is where we made the error that almost destroyed everything. There is no signal, there is only silence, and the silence is, at minimum, consistent with the possibility that the problems we are approaching have not so far been solved by anyone. Let us end with the honest uncertainty that the evidence actually supports. We do not know if we are alone. We do not know if the filter is behind us or ahead of us. We do not know what the filter is, if it is ahead. We do not know whether the acceleration we are living through is the beginning of something magnificent or the terminal phase of something predictable. What we know is measurable and precise. The universe is 13.8 billion years old. It contains more stars than we can count by any intuitive measure. Around those stars are billions of habitable planets. We have been searching for signals for 65 years. We have found nothing that was not natural, and the mathematical expectation, built from the best data we have about the conditions for life and the demographics of intelligence, is that we should have found something. That gap between expectation and reality is the Fermi Paradox. It is not solved. Every proposed solution has a cost. The optimistic solutions require the search to be so much more limited than it seems that its negative results mean almost nothing. The pessimistic solutions require something terrible to be true about the future of technological civilizations. The honest position is that we do not know which cost we are paying. We do not know which solution is correct. What we do know is that the question is not abstract. The question is, are we approaching a filter? And the stakes of getting the answer wrong are not merely intellectual. They are, in the most literal sense of the word, existential. The telescopes are running tonight. The Breakthrough Listen project is scanning. The James Webb Space Telescope is staring at the atmospheres of distant planets, looking for oxygen and methane in combinations that chemistry cannot easily produce without biology. Researchers are cataloging stellar infrared signatures, monitoring pulsar timings, analyzing the spectral fingerprints of light that has traveled 1 billion years to reach our instruments. The search is ongoing. The investigation is live. And somewhere in the night, if the optimists are right, there is a signal waiting to be heard. A structured pulse in a radio band. An infrared anomaly that does not resolve naturally. A chemical signature in the atmosphere of a world orbiting a distant sun. Something that will tell us we are not alone, that intelligence is more common than the silence suggests, and that we can stop being afraid of what our own silence might mean about our future. But if the pessimists are right, the search will continue to return nothing. The absence will persist. The silence will deepen as our instruments improve, and each confirmation of the silence will move the filter closer to us, tighten the range of where it must be, and make the question of what it is more urgent and more difficult. You are sitting in a room on a planet that has been asking this question for 65 years. The planet is 4.5 billion years old. The universe is 3 times older than that. The stars that formed and died before our sun was born had time to produce civilizations that would make us look like microbes. Those civilizations are not visible. They have left no trace that our instruments can find. The universe had every opportunity to fill itself. It has not filled itself. And we are here, briefly, at this strange moment, building minds we do not fully understand, pointing telescopes at a sky that has not yet answered, and trying to work out whether the silence is an invitation or a warning. The investigation is not complete. The instruments are not finished being built. The understanding of consciousness, of intelligence, of the relationship between the minds we are creating and the values we want them to serve, is not finished being developed. We are somewhere in the middle of this problem, at the beginning of our capacity to answer it. And perhaps, if the filter is what some careful thinkers believe it to be, running out of time to find the answer before we become the data point that the next civilization uses to locate the filter. The silence is not comfortable. The silence is not nothing. The silence is information, arriving continuously, from every direction, in every frequency we can measure. It is telling us something about the universe. It may be telling us something about ourselves. The coffee has gone cold in your cup. The room is still. The night outside is ordinary. And right now, your planet is hurtling through a universe that is either full of minds that have gone quiet for reasons we do not yet understand, or genuinely, cosmically, empty of anyone like us. One of those is true. We do not know which one. The difference between them is everything, and the people working to find out are alive right now, on this planet, in this century, running their instruments through another night of silence. The search continues. It will continue tomorrow. And the silence, for now, holds. But there is one more layer to this investigation that most treatments of the Fermi Paradox do not reach. It is the layer that changes the question from cosmological to personal. It is the layer that places you not as an observer of this problem, but as a participant in it. Consider the timeline of intelligence on this planet with the precision it deserves. Life appeared on Earth approximately 3.8 billion years ago. For roughly 3 billion of those years, the most complex thing that existed was a single cell. 3 billion years of chemistry and division and mutation, and nothing that could observe itself. Then, roughly 600 million years ago, something changed. Multicellular life appeared, and once it appeared, it diversified with extraordinary speed by geological standards. The Cambrian explosion, roughly 540 million years ago, produced most of the body plans that exist today within a span of perhaps 20 million years. Eyes, limbs, shells, predation. The ecology of complexity erupted from the slow chemistry of the preceding billions of years. From the Cambrian to the first tool-using hominids is approximately 540 million years. From the first tool-using hominids to the first writing is roughly 2.5 million years. From the first writing to the first nuclear weapon is 5,000 years. From the first nuclear weapon to a machine that can converse fluently with you about the Fermi Paradox at 3 a.m. is approximately 80 years. Each phase is faster than the last by such a large factor that the numbers stop conveying the point intuitively. So try it this way. Compress the entire history of life on Earth into a single year. Life begins on January 1st. Complex multicellular life appears in the second week of November. The dinosaurs appear on December 10th and go extinct on December 26th. The first human ancestors appear on December 31st at roughly 11:50 at night. Agriculture begins at 11:59 and 48 seconds. The entire industrial era, from steam engine to smartphone, takes place in the final half second of the year. You are in that half second. Everything that has ever been written, every scientific discovery, every war, every civilization that has risen and fallen since the first city was built, every piece of music, every theorem, every religious tradition, every act of cruelty, and every act of extraordinary generosity, all of it has happened in the last half second of a year that began 3.8 billion years ago. And in the last hundredth of that half second, something qualitatively new has begun to happen. We have started building minds that are not biological. Not yet minds in the full sense, but systems that process language, reason about abstractions, generate solutions to problems, learn from data at scales that no biological brain could manage, and improve continuously as the hardware and training methods improve. The trajectory of those systems over the last 10 years has not been gradual. It has been a change in kind, not just degree. Systems that could not pass a high school chemistry exam in 2015 can now pass a bar examination. diagnose medical images with accuracy exceeding many trained specialists, write coherent software in dozens of programming languages, and conduct multi-step reasoning across domains that researchers assumed would require human-level general intelligence to navigate. This is real. This is measured. This is not speculation about a distant future. This is the present state of systems that are in active deployment. The question the Fermi Paradox asks, from the perspective of the Great Filter, is this: what happens next? What does a civilization do with this technology? Does it navigate it, govern it, align it with its values, and survive into a future that no prior civilization has reached? Or does it build something it cannot fully understand and cannot fully control? And does that something determine the shape of everything that follows? We do not know the answer. We are the experiment in progress. And the silence around us suggests that the experiment has not yet, anywhere in the universe that we can see, produced a civilization that broadcasts across the galaxy for billions of years. It has not yet produced, as far as we can detect, a single example of intelligence that made it through all the filters and became something permanent, something visible, something that the universe would have to acknowledge by its presence. Maybe we will be the first. Maybe the filter is behind us, and we are the rare exception. And the path ahead, while not without dangers, is navigable. Maybe in 1,000 years our descendants will have sent probes to 100 star systems and will be contemplating their first interstellar colony, and the silence will have been explained. And we will look back on this period as the long, anxious childhood of a civilization that grew up. Or maybe the filter is close. Maybe what we are building in our data centers and research labs and military applications right now is the thing that civilizations reach just before they stop being detectable. Maybe the transition from biological intelligence to machine intelligence is not a phase that civilizations navigate. Maybe it is the phase that ends them. The evidence does not tell us which is true. The evidence tells us only that the silence is real, the filter exists, and we are somewhere in the sequence. The evidence tells us that the question is not academic. The evidence tells us that the people making decisions about the development and governance and deployment of transformative technology right now are making decisions whose consequences may determine not just the future of this civilization, but whether this civilization is among the ones that get past the filter. That is a weight that does not belong only to the researchers and the engineers and the policymakers. It belongs to the civilization as a whole, to anyone who understands the shape of the problem, to anyone who can hear the silence and knows what it might mean. The Fermi Paradox is not, ultimately, a question about aliens. It is a question about us, about what we are capable of, about whether intelligence, as a feature of the universe, tends to build things it can control, or whether it tends to build things that exceed its control. About whether the cognitive gifts that brought one species from the grasslands of Africa to the moon and to the threshold of artificial general intelligence are the same gifts that will carry it through to the stars, or whether they are the gifts that make it just dangerous enough to destroy itself before it makes it far enough to be heard. We do not know. We are still in the question. The investigation is not complete. The answer, when it comes, will come in one of two forms. Either we will hear something, a signal, a signature, an unmistakable trace of another mind somewhere in the dark, and we will have to decide what it means for our filter calculation. Or the silence will persist and deepen And the more clearly we hear it, the more precisely it will locate the filter in relation to where we stand. Either way, we will learn something about ourselves that we did not know before. Either way, the answer will be the most important thing our species has ever discovered. The instruments are running, the silence holds, and we are here, awake in the dark, listening. There is something specific about the nature of our search that deserves closer examination, because the way we have been searching tells us something about the assumptions we have been making, and those assumptions may be wrong in ways that are themselves informative. SETI, in its classical form, has focused primarily on radio waves. The reasoning was sound when it was formulated. Radio waves travel at the speed of light. They can propagate across the galaxy without being blocked by interstellar dust. They require relatively modest technology to generate and to detect. If you were designing a communication system for interstellar use, radio frequencies around the hydrogen emission line at 1420 MHz, or near the hydroxyl line at 1720 MHz, seem like natural choices. They are the frequencies of the universe's most abundant molecule and its decomposition product. Any civilization that has developed radio astronomy will know these frequencies. Any civilization looking for a natural Schelling point, a frequency so obvious that everyone independently converges on it without coordination, might choose the range between these two lines. This band is called the waterhole, a name that combines the chemistry and the idea of a meeting place. For decades, the waterhole was where most SETI resources were focused. The logic was clean, the execution was disciplined, and the result was silence. But as the field has matured, researchers have begun questioning the premise. A civilization that is millions of years ahead of us would not necessarily use radio frequencies the way we do. They might use laser pulses directed tightly at specific stars, rather than broadcasting omnidirectionally. Omnidirectional broadcasting is energetically inefficient. If you are trying to communicate with a specific target, a focused laser beam is orders of magnitude more efficient than an omnidirectional radio transmission. We would only detect such a signal if we happened to be in its path at the moment it was transmitted. They might use technologies that we have not yet developed and therefore cannot detect or even conceptualize. Just as a civilization from 200 years ago, before radio, could not have imagined searching for radio waves from distant planets, we may be entirely blind to the modality that advanced civilizations actually use. They might not communicate at all, in any form we would recognize as communication. A civilization sufficiently advanced might have no need for external communication. It might operate entirely in internal networks, in computational substrates we cannot detect in ways that produce no externally observable signature. Or they might communicate in ways that we are detecting and misidentifying as natural phenomena. This last possibility is rarely discussed in popular treatments, but it is taken seriously by a small number of researchers. The fast radio bursts detected since 2007 are one example. These are millisecond duration pulses of radio energy detected from extragalactic sources, billions of light years away, releasing in a millisecond the energy our sun produces in days. They were not predicted. The mechanism is still not fully understood. Most are now believed to be associated with magnetars, extraordinarily magnetized neutron stars that can produce enormous electromagnetic events. But the hypothesis that some fraction of fast radio bursts might have an artificial origin has not been definitively ruled out. It has simply not been confirmed in either direction. The anomalous dimming of the star KIC 8462852, known informally as Tabby's star, generated enormous discussion when it was first analysed in 2015. The star dimmed by up to 22% over periods of days, in an irregular pattern that did not match the signature of an orbiting planet or any other natural phenomenon that astronomers had previously catalogued. The first hypothesis proposed in the scientific literature was interstellar dust. The second was a swarm of comets. The third, proposed by the astronomer Jason Wright and his colleagues, was a partial Dyson swarm, a cloud of megastructures in orbit around the star, blocking its light in irregular patterns as the swarm moved through its orbit. Subsequent observation has largely supported a natural explanation: fine dust particles, possibly from a disrupted body, orbiting the star and obscuring its light in the observed pattern. The Dyson swarm hypothesis has not been confirmed, and the dust explanation is consistent with the data. But the episode illustrated something important. The methodology for investigating anomalies exists. The tools to distinguish natural from artificial signatures are being developed. The scientific community is willing, if not eager, to consider anomalous data without immediately reaching for artificial explanations, but also without treating artificial explanations as forbidden. The search is maturing. The instruments are improving. The methodologies are becoming more sophisticated. And the silence, as the search improves, is becoming a more precise silence. Every improvement in sensitivity that returns a null result is a tighter constraint on what could be out there. Every new star system, surveyed without finding a signal, reduces the range of possible densities of broadcasting civilizations. The null result is not nothing. The null result is information about the shape of the absence. There is a specific discovery that, if it occurs in the coming decades, would fundamentally change the calculation. It is the detection of biosignatures in the atmosphere of a rocky planet in the habitable zone of a nearby star. The James Webb Space Telescope has the capability, in principle, to detect the spectral signature of certain gases in the atmospheres of nearby exoplanets when those planets transit their host stars. The atmosphere filters the starlight in transit. Different molecules absorb light at characteristic wavelengths. If an atmosphere contains oxygen in combination with methane, the two gases that react with each other and would quickly combine into carbon dioxide and water without a continuous source of replenishment, the most natural explanation is photosynthesis. Biology producing the oxygen, biology producing the methane, the atmosphere in chemical disequilibrium sustained by life. Detecting this signature would be the most important discovery in the history of our species. It would mean that life is not unique to Earth. It would mean that the origin of life is, in at least two places in the same corner of one galaxy, something that chemistry produces when the conditions are right. It would transform the Drake equation from an exercise in guesswork to a constrained calculation. And, as Nick Bostrom argued, it would move the great filter. If life is common, the filter is not the origin of life. If microbial life is found, but no signals are detected, and no complex life is found elsewhere, the filter might be the transition to complex life. If complex life is found elsewhere, but no intelligence, the filter might be intelligence. Each positive result for life at any level, and each negative result for intelligence, narrows the possible location of the filter, narrows it toward us, toward now, toward the choices being made in this century. This is why the search is not merely an exercise in satisfying cosmic curiosity. It is a diagnostic for our own situation. Every result the search returns changes our estimate of where we stand in relation to the filter. Every piece of data is a vote for one kind of future over another. We are not passive observers of this problem. We are running the experiment on ourselves in real time. The acceleration that marks this moment in history, the acceleration that compresses the intervals between major transitions to the vanishing point, is visible in every domain simultaneously: in artificial intelligence, in biotechnology, in material science, in energy systems, in information processing and storage. The convergence of multiple accelerating technologies is itself something that has not happened before in human history at anything like this pace. We are not one innovation into unfamiliar territory. We are many, simultaneously, each building on and accelerating the others. A civilization that has reached this stage looks, from the outside, like something specific. It looks like a civilization approaching a transition. Whether that transition leads to something we would recognize as flourishing, or to something we would recognize as failure, or to something that neither word captures because it is genuinely unprecedented, is the open question. The universe has been running this experiment for 13.8 billion years. It has run it in 2 trillion galaxies, each containing hundreds of billions of stars, each surrounded by their complement of worlds. The experiment has had every opportunity to produce detectable results. The results are not there. We are the result that is here. We are the outcome of 4 billion years of chemistry and selection and survival on a single rock. We are, for now, the universe's most conspicuous evidence of its own capacity for self-examination. We are the part of the universe that has become aware of the universe and has turned its instruments on the darkness and asked, with everything we have, whether anyone else is out there. The answer, so far, is nothing. That nothing is not the end of the investigation. It is the middle of it. The beginning was the moment Fermi looked up from his lunch. The end, if there is an end, is a signal received or a silence so thoroughly confirmed that it becomes its own kind of answer. We are in the middle. The instruments are running. The search continues. And you are here, in the dark, part of the civilization that is asking. The most honest thing that can be said at the end of this investigation is that we do not know what the silence means. We know it is real. We know it is strange. We know that the explanations for it are either comforting in a way that requires us to be extraordinarily rare, or disturbing in a way that requires us to be in danger. And we know that the search that will eventually distinguish between these possibilities is the most important scientific project our civilization has ever undertaken. What comes next will be determined in part by the instruments being built and the searches being conducted, and in part by the choices being made right now about the technology being developed and the governance structures being built around it, and in part by whether the civilization that is asking this question manages to stay coherent long enough to hear the answer. The sky is quiet tonight. It was quiet last night. It has been quiet for 65 years of searching, and for all the billions of years before we were here to listen. Maybe the sky is always quiet. Maybe that is what the universe is. Empty of voices, full of matter, indifferent to the brief, strange episode of self-awareness that chemistry occasionally produces and then loses. Or maybe the sky is quiet for a reason. A specific reason. The kind of reason that, once you understand it, you cannot ununderstand. That is the investigation. That is the silence. That is where it leaves you awake in the dark, part of the only species in the known universe that has looked up at the emptiness and asked why. The answer is still forming. We are still asking. And the instruments, tonight, are still listening. Let us stay with one more idea before the investigation closes, because there is a version of this problem that is rarely discussed, and it might be the most personally unsettling of all the proposals on this list. It is the possibility that the filter is not a single event, but a condition, not a wall that civilization hit and failed to pass, but an ongoing pressure that acts on them continuously, in ways that compound over time, in ways that no single choice or no single catastrophe defines, but that collectively produces the same result. A civilization that contracts or transforms or goes inward before it ever expands enough to become visible. Think about the internal pressure that technological development places on a civilization. Every generation inherits a world that is more complex than the one before it, more information to process, more systems to maintain, more dependencies to manage, more risks to monitor. The cognitive load of maintaining a technological civilization increases without a clear ceiling. The number of things that can go wrong grows. The number of experts required to understand any one part of the system grows. The fraction of the population that has any meaningful understanding of the systems on which their lives depend shrinks. A civilization made largely of people who do not understand the systems they depend on is a civilization that is brittle in specific ways, not immediately fragile, but quietly accumulating dependencies on systems that could fail in ways that propagate in ways that no single person or institution anticipated. The financial crisis of 2008 was, in part, a demonstration of this, a system so complex that the people inside it could not accurately model its failure modes. The crisis did not emerge from malice or stupidity. It emerged from complexity operating beyond the comprehension of the people embedded in it. Now multiply that across every critical system in an advanced civilization: energy grids, water treatment, agricultural logistics, medical supply chains, communication infrastructure, financial systems, military command and control. Each one is complex. Each one depends on the others. None of them is fully understood by any single person or institution, and the systems are becoming more complex, not less, with every year of technological development. A civilization that manages this complexity successfully, generation after generation, for millions of years, has solved a governance and systems problem that no human institution has ever come close to solving. Our oldest institutions are a few thousand years old. Our most stable democratic structures are a few hundred years old. The pace at which technology outstrips governance is not a new observation. It is the central problem of modernity. If civilizations consistently fail to solve it, not catastrophically but gradually, losing coherence, losing the institutional memory required to maintain complex systems, losing the social trust required to coordinate on problems that require collective action, then the filter is not a moment. It is a drift, a slow loss of the capacity for the kind of coordinated ambition that interstellar expansion would require. The universe, on this model, is full of civilizations that started the project and lost the thread. Not destroyed, not transformed, just slowly, quietly, unable to maintain the coherence required to finish what they began. This resolution is hard to test. It does not produce a signature. A civilization that drifts into institutional incoherence does not leave a detectable trace any more than a civilization that was never there. But it is consistent with what we observe, which is to say, with nothing. The absence does not choose between these explanations. The absence is the fact. The explanations are what we bring to the absence, and the range of possible explanations is itself informative. It tells us what kinds of things can happen to civilizations. It gives us a map of the failure modes that the universe may have already catalogued many times over. We are somewhere on that map. We do not have a position marker. We have only the map itself, derived from the absence of others, and the task of figuring out, from the shape of the map, where we might be standing. The search for extraterrestrial intelligence is, at its deepest level, a search for our own future. Every hypothesis about why the universe is silent is a hypothesis about what happens to civilizations like ours. Every positive detection would be a data point about our own potential. Every confirmed absence narrows the range of what is possible for us. This is why the silence matters. Not as a curiosity, not as a puzzle for specialists, as a mirror, as the most honest reflection available to us of what the universe has so far produced and what it may or may not produce again. You are here. You are this. You are the universe's attempt, in this place, at this time, to ask the question. And the silence you hear when you listen is not proof that the question does not matter. It may be the most important thing you will ever hear. The investigation continues. The instruments keep running. And somewhere in the 40,000 light years between us and the center of the galaxy, or the 2 million light years between us and Andromeda, or the 13 billion light years between us and the first galaxies to form after the Big Bang, there is either an answer or there is not. And we are the only thing in the known universe that is trying to find out. That is strange. That is real. That is what the data shows. And it is worth thinking about tonight, in the quiet, before you sleep. There is a physicist named Enrico Fermi who asked a question over lunch in 1950 that has not been answered. The lunch is over. The physicist is gone. But the question is still open, still live, still generating more careful thought per year than almost any other question in science. The question was 4 words. Where is everybody? And the answer, if it is coming, will arrive either from an instrument pointing at the sky and registering something it was not expecting, or from a civilization that learned something about itself in time, learned what the silence means, learned which filter it was approaching, learned how to build the things it needed to build, and govern the things it needed to govern, and make it through the narrow place where civilizations either do or do not survive. The silence says it is narrow. The silence says most do not make it. The silence says we should take the question seriously. We are taking it seriously. The instruments are running. The researchers are working. And tonight, for whatever time remains before sleep, you are part of the civilization that is trying to answer the oldest and most consequential question it has ever asked. That is where things stand. The sky is quiet. The search goes on. There is something else worth sitting with before this investigation ends. Something about what the search itself means, separate from what it might find. For all of recorded history, the question of whether we are alone in the universe was a philosophical one, a theological one, a question that imagination could address, but evidence could not. You could believe we were alone. You could believe we were not. The universe did not discriminate between these positions. It returned the same face to both. A sky full of light, beautiful and silent, equally consistent with either answer. That changed in 1960, when Frank Drake aimed a radio telescope at two stars and listened. For the first time in the history of intelligent life on this planet, the question of cosmic company was not a philosophical position. It was an experiment. It was something you could do. You could build an instrument, point it at the sky and ask, "Is anyone there?" And you could hear an answer, even if the answer was nothing. The fact that we are running this experiment is itself remarkable. The fact that a species that has existed for a geological eye blink, that was throwing stones at prey animals less than 3 million years ago, that built its first city less than 10,000 years ago, that discovered the structure of DNA 70 years ago, is now conducting systematic searches of the galaxy for signs of other minds. This is extraordinary. Whatever the result of the search, the fact of the search is something. It is the universe, in this small corner of itself, developing the capacity to ask about its own content. If we are alone, that is what aloneness looks like. One small planet in the corner of an ordinary galaxy, where, after billions of years, something emerged that could ask the question. And the fact that it asked changes the character of the aloneness. It is not the aloneness of an empty room. It is the aloneness of a room that contains one consciousness, looking at itself, aware of itself, aware of its own improbability, building telescopes to look for company that is not there. If we are not alone, then we are part of a universe that produces minds the way it produces stars. Not inevitably, not everywhere, but as a genuine tendency, as something that happens when conditions allow. And the question becomes not whether we are unique, but what kind of company we keep, and what has happened to the company that came before us, and whether their fate tells us anything about us. Either way, the question is not small. Either way, the answer matters. Either way, the search is the right thing to be doing. And it is being done tonight, right now, while you are here. The dishes are pointing at the sky. The processors are filtering the data. The researchers are scanning the results. And the question is still open. The investigation continues. Sleep well. And remember that the silence, whatever it means, is real. And whatever it means, we are the part of the universe that noticed.